Hey folks, welcome to Advent of Code in F Sharp day 12. I'm running a bit late today, so the puzzle has already unlocked. Not a problem. Let's take a quick look. Passage pathing. Ooh, this sounds like a graph algorithm. With our submarine's subterranean subsystem subsisting suboptimally, I felt like I was in a test there. The only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path. Is this a hint? The only way to know if you found the best path is to find all of them. Fortunately, the sensors are still mostly working, and so you build a rough map of the remaining caves, which is our input. This is a list of how all of the caves are connected. So nodes are caves, and edges are connections between caves. Cool. You start in a cave named Start, and your destination is a cave named End. An entry like BT means that blah blah blah. That makes sense. So this is the map of the provided example. Start only goes to A and B. Yeah, okay, makes sense. Your goal is to find the number of distinct paths that start at start, end at end, and don't visit small caves more than once. There are two types of caves, big ones and small ones. It would be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting them multiple times. Okay, so we have two types of caves. Some of them we can only visit just the once. Other ones are you can pass multiple times. That's an interesting twist on the problem. All paths you find should visit small caves at most once, and can visit big caves any number of times. Given these rules, there are some paths from start to end always. Yep. Each line in the above list corresponds to a single path. Okay. Now note that in this cave system, cave D is never visited by any path. Yeah, that's a dead end. To do so, cave B would need to be visited twice. Yeah. Slightly larger example. Why is this? This looks like the text is changing color for my eyes, so maybe I'm tired or maybe something funky is going on with my screen. Okay, but we have a larger example. Okay, with 19 paths, and then there's this even larger example with 200 something paths. We get 3 different examples of growing size that does not bode well. Okay. That sounds reasonable enough. Let's grab our input. Let's put it somewhere. Interesting. Interesting. Let's take a look at that again. So, okay, yeah, edges are not directional. If you can go from one to the other, you can go from the other to one. And I think we have to kind of do that. Definitely do that because the start edge is on the right for 3 times in our input. Let's take a look. Is this in one of the examples as well? No. Yes. Okay, it's also in one of the examples, so we'll catch it. We need to count. Yeah, we need to count the total number of paths, so we don't have to optimally search for. If you can enumerate all the paths, I'm wondering already, what could part 2 be? If the search space is small enough to enumerate all paths in a reasonable amount of time. Interesting. Okay, how will we do this? It doesn't really matter which kind of search algorithm we use, right? If you do depth first or breadth first or whatever first, we need to find them all. Yeah, so I'm gonna do the first thing that flows out of my fingers and not worry too much about that. Yeah, and just do a brute force search. We just take the start node, we look up every next node we can visit. Maybe keep track of a list of small caves we visited, because we can only visit those once. And then just start working down the list, start working down the paths until we reach end. Oh, I think that's it. Cool. Let's grab the first example. I'm thinking a bit, how should we parse this? What will we be doing with these things? We need to find, or we need two bits of information from this. One is the caves or the nodes. Next, we need to know whether it's small or big. And the third piece of information is the pathways we have, or the edges from one cave to another. Okay, let's start modeling. So we have caves, which are small or large, big. I don't remember the exact wording used. Big caves, yeah, and small caves. What will we be building? We just need a list of all the caves, whether big or small. And we need a list of, or no, an easy way to access accessible paths, or one steps paths, paths of one step of length. That's a very hard thing to say at 6 o'clock in the morning. But I think if we know those two kinds of things, if we can parse that out of the input, we are good to go. So let's do that. I'm writing the function already. I'm just gonna play with the example first. So parse edge. What is the official term for this thing? Parse connection. Yeah, let's call it parse connection. So we need to split on the hyphen. Or we can even stay in the character split thing. Yes, we can. So that is a one and the other. Let's just extract those two directly. Where is my closing rec? Okay. So those are the two caves. Those are both strings, yes. So actually it makes no sense to have a big of character and a small of character, because end and start are both small caves, and I don't like seeing this asymmetry because it will make our lives harder. Let's keep everything a string instead of a single character. Okay. What do we need to do? We need to parse. Let's just parse a connection out of this. So just doesn't really have to be directional. Let's just parse this as a tuple for now. So one another, and the only extra thing we need is we need to know whether it's a small or a big cave. What can we do with a string that helps us with stuff like this? We have nothing. Do we have something on character? I remember there being something called uppercase, upper stuff. Where is it? We could do something like 2 uppercase. No? Where is it? To upper? Okay, you can do to upper, but that's not really what I want to do. Ah, there's a character dot is upper. Indicates whether the specified Unicode character is categorized as an uppercase letter. Yeah, we can use that. So this is the, let's call it write a function called parse cave. Which parses our string into a cave, and let's write that function. So if cave first character we meet, if it's an uppercase, we have a large one. So if cave first, if the first letter of a cave is an uppercase, we have a large cave. Oh dear. Well, my computer is being a bit slow today. Okay, there we go. Upper, that's a big cave. Otherwise, it's a small cave. We have just successfully parsed. I think so. Let's take a look. So we have a small cave called start and a big cave called A. That looks good. Let's take a look at the end one. Yeah, that looks good. One more thing I want to do. We have like a list of tuples of caves. That's a useless data structure. It's not useless. I want to build a quick lookup table so we can look up adjacent caves for a given cave. I think if we build a single map, mapping what we just parsed and the inverse of what we just parsed, we can do that quite efficiently. Yeah, so let's call this connections, or yeah, let's call this connections for now. So this is just the flat list we just parsed, and now let's make that into something more interesting. So connections, list append, is that the thing to add the second list? Yep. And we append the same thing but reversed. So something like this. What is not, something is not happening here? What's the problem, dear compiler? Oh, it's not a list, it's an array. My bad. So this should be both. I don't know why, but I'm just gonna drop in a distinct here. It's not even necessary because we have no loops to itself. And every step takes a step away from the node we visit. Yeah, that's not useful. But we can plop this into a map. I'm just gonna call that the very intention revealing name lookup. So this now contains a lookup table that maps. No, that's not correct. It only maps just one, and that's not what we want. Sorry. We need to group by. This will be better. Let's see what we get from this. Yeah, so this is a... do we have a case? Yeah, big A here has multiple nodes going out of it. Start, end, C, and B. So this is okay. And let's now build a list from this. So we have the from, and we have a list of tuples, which are the toes. I'm going to call them toes just for fun. And the thing we want to return is from, and from the toes, we extract the second part. So that's sequence dot map and then the second part. Visual Studio, why are you giving up on me today? Something like this. And if we put that in a map, we are actually where we wanted to be, I think. And I'm gonna make this an array or a list. What is twos? That's a list syntax, I guess. No? No, that's array syntax. Okay, let's keep it an array then. So let's verify this manually. We have a small b that's connected to start and a and d. Start a d and end. Yeah, looks correct. Start has only a and b. Yeah, we're good. We're good. So this is our lookup table. This is... Oh, we still just need the nodes. I'm going to call it caves. I'm going to use a collect, I guess. So we can loop over the pairs and return a list containing one and other. So we just take a tuple, make it a 2-element list. Okay, we want to stay in the array world. I don't know why. Does array need to return array? Yeah, and it takes an array as well. Okay, yeah, kind of makes sense. So these are all the individual cases, but we have duplicates, I guess. Small start, small c, small b. Yeah, we have duplicates, so let's just dedupe that with a distinct. These are all the vertices we have, or all the caves, sorry. Yeah, makes sense. Now we can start writing our algorithm, or pathway finding algorithm. What just happened? Was this an auto format delay? Okay. Anyway, what will the pathway finding algorithm look like? We just grab start node, look at all the neighbors. Breadth first or depth first? Doesn't matter for the first part. So we're just gonna do whatever feels natural. So this is our starting node, let's say. Let's look up neighbors. That's a lookup in lookup. So map.find our current cave. We should be able to navigate from start to A and B. I think that is correct. Yep. And we also need to keep track of the visited caves, or caves that are already part of the path, or we need to do that at least for small caves. Yeah, we need to keep track of the small caves we visit for each and every path. Let's do that with a set that gives us faster performance looking for an element, or whether a set contains an element is way faster than doing the same with a list. So we have a set of small caves we have already visited. Then we just grab a path and we look at where we are in that path. We grab all the neighbors and then we just recursively descend down all those paths. Right? Right. It's a bit early for me. My brain is heating up, so I'm a bit slow on the uptake for this part of the algorithm. So let's take a step back because my mind is not grokking the problem here. What are we actually trying to do? Find paths. So we'll have something called find paths in the end, maybe, if we feel like it. What do we get? What's the data structures we have? Lookup with all the direct connections. List of caves. I don't know if that's actually useful. I don't know why I built this. No, we probably won't even need this. We only need the lookup table. So we'll have a function called find paths, which takes a lookup. Will it be recursive? Somewhere in there we'll need recursion. And then we do the thing we're doing. How do we know what the current node is? This is the start node, so we can just hard code that part. Yeah, I'm stuck, so I'm just gonna doodle on in the REPL, play around with the problem a bit until I start to see the light. So what am I going to do? I'm just gonna grab current, and I'm gonna take a first step for current, which is actually exactly what I've been doing. So these are the two paths we can take. Do we actually need to know the path? Do we need to keep track of the path itself? Am I dropping frames? No. But my computer is really hogging some resources. Let me take a quick look at what's happening. It's that system file checker thing again. Great. And I cannot kill it. Okay then. Then let's just continue. Do we need to keep track of the path itself? Or its length, or whatever? I don't think we need to for part 2, but we need to find distinct paths. So yeah, let's keep track of the path. Just trying out something here. So let's say we keep track of the paths, and by the way, it's maybe from every new element gets prepended to the front of a list. Maybe that's enough of a data structure for now. Won't we have like infinite loops, or maybe the problem catches that for us? If you have enough big caves, I think you could potentially loop the loop. Yeah, the problem doesn't mention anything like that, so probably we're fine. But for every neighbor, we need to do something. Yeah, so maybe let's map over neighbors. Neighbors is what? An array of caves, cool. I'm just gonna build the current paths. And this is something we actually cannot do if this single neighbor, if we already visited it and it is a small cave. Right. So if small caves visited contains this neighbor, we don't do anything. So that's a not here probably. So only take neighbors that are not in this set. Yeah, and then, okay, we have a valid neighbor to cross. And then we have multiple paths. That's something that's not okay in the current algorithm, because we just take a starting node instead of a starting path, but we'll get there. Yeah, this looks okay enough. Yeah, no, this will work. We need to do more than just map. Yeah, we need to do more than just extend the path. We also need to do the bookkeeping with the visit caves thing. We need to do that per path. So let's just dump that into a recursive call. And the recursive call does not need a node, but a path. So if we do this probably. That's the current path. And if we call, do we only have one path? Yeah, we do. Let me just refactor a bit. So we have a current path, and current is just current path. The last element we added, so that's the most recently visited node of that path. Click, 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 click. Then everything is starting to fall into place. Yes. Only thing we need to do is small case visited. That needs to go into the recursive call as well. So that needs to be somewhere down here as well. Let's start writing a function. So let's write a function find paths from, given a path and a set of visited small caves, and that will return a sequence or a list of something, and the something is actually we don't need to return anything else than a list of paths, because the small case visited thing is just a utility thing. I think this is good enough. Yeah, only we need to do the recursive call. How do we know when we're done? If we reach end. Or we could do, if we don't find, because maybe not everything ends. No, not everything ends. Even in the small example, there was a dead end. So if we can't move anymore, or if we reach end, we are done. Yeah. Is that saying the same thing? No, we could infinitely jump out of end to A and back to end, but that's not something we want to do. So we are done if path current. If current is a end, then we're done. Or if we find no neighbors to move to, which is this part. Yeah. Let me just grab this and put that into the neighbor variable declaration. So that's actually the thing we want to look at. Only problem we have with let me just satisfy the compiler for a bit. Cool. Only problem we have here is this map.find thing will crash if we don't find. But we always will find something, right? Every node is connected to at least one other node. Yeah. But this set of small visited caves thing can filter out everything, so we end up with an empty list. So our halting condition for this recursive function is if neighbors, if we have no neighbors anymore that are eligible to go to, or if our current node equals the end cave. Can I do or in English? I've seen colleagues do this for C#, so let's give it a try. And we are generating lists of alternatives, so let's wrap path into a list. Otherwise, we need to do something else. Does this look correct? Or does not look correct? In F# code used pipe. Okay, we will do that. Sorry, compiler. Does this still make sense? Yeah, I'm gonna grab these two variables and move them out because they're actually not part of this function. They're part of the initial call. And then we just need to use this one. Okay, we're good. I'm gonna call this current cave to make it more clear what we're doing. So a function find path from given a starting path and a set of small caves visited for that path. Find where we are right now, look up where we can go. Oh, by the way, we could do this earlier, but I don't think performance will be an issue. No, you know what? I'm gonna do this before because I don't like the formatting I'm seeing here. So if we are at the end, then we're done. Otherwise, figure out some neighbors. Oh, by the way, if we have no eligible neighbors, then we're done. Otherwise, and that's where the interesting part happens. I don't know if this nested if thing, whether or not I like it, but I don't care. Let's just keep going for a while. At least I like the auto formatting I'm seeing here a bit better. So next is actually almost correct, but we need to do recursive calls, and for the recursive calls we need the updated set of visited small caves. Yeah. So this is almost correct, except that it doesn't keep track of small caves. Yeah, so let's keep track of small caves. Small caves only need small caves, so if n is a big old cave, we don't need to do anything. Otherwise we need to append it to small caves visited. So let's write an append. It's tricky enough to extract it into its own function because we have two different types of caves. So match cave with if it's a large cave. Did we call it large? No, we called it big something. Yep. If it's a big cave, the set of visited small caves is okay. If it's a small cave, then we can add it. So this is a helper function which we can use here. I'm just gonna go YOLO and do the recursive call without even inspecting what I'm doing. So we need a new list of small caves, which is the original set where we do this helper thing with the new visited cave. I think this might actually be it. What is not okay? Am I missing? Yeah, I'm messing up some parentheses. That's the problem. And this returns a list of a list. Yes. So if we collect, that should make everything better again. No, it does not. Is it because we are working with arrays versus lists? Should I make this an array instead? Okay, if this does not satisfy the compiler, I will take an actual look at the problem instead of guessing my way out of here. Okay, I think this is almost good. This is set of cave. The type set cave does not match the type cave. Sorry? Oh yeah, I need to switch argument order here. Yeah, that's better. In my head at least, this kinda is the algorithm for part 1. So let's give it a shot for the example. To start this thing off, we need to provide this path and this set. Yeah, that looks correct. So find paths from current path using the small caves we already visited. And that should actually give us all the paths without looping. First time right. Let's give it a go. No, it's crashing. Oh no, it's just these two. I'm just gonna send everything to my REPL again just to be sure. Hey, that looks actually not too shabby. It's generating a lot of duplicates. That's how can we fix that? We can just ignore the fact that we're generating a lot of duplicates. But I think performance-wise, this duplicate thing might burn us. Is it correct that we have 1, 2, 3 paths? No. It's definitely not correct. Interesting. For some reason, they're all like, they don't even start at the start. I don't even understand what this output is showing me. Current path is small start. We have not visited any small caves. That's actually not correct. Small is a small cave we visited, right? I think so. Let's do it a bit differently. Let's do it like this, yeah. But I don't think that will be the actual problem, will it? No, not at all. Where did our start go? What is happening? Current cave is this. If it's the end, then we're done. Otherwise, look up neighbors. Yeah, let's start printing out stuff. I don't see the problem. Wait, if we lose start, that means we are not using current or path correctly. Oh dear, this is the problem, right? Yeah, this is not the entire path. We need the entire path down here. So let's just append the next node to the entire path. That will work heaps better. Let's give it a go now. Come on, CPU. I'm not asking a lot. I'm just asking you to type. Okay. Close but no cigar. We need 10 paths. Okay, let's print them out. And let's see which paths we're including that are not supposed to be in there. I'm gonna reverse every array for a sec, so we can troubleshoot more easily. It's a list somewhere down. Oh yeah, there we do list concatenation. The cons. Okay. Somehow we missed, probably we missed 2 paths. How could we have? Oh no, sorry, we have too many. We need 10, and I thought we had what, 13? Yeah, we have 13, so we have 3 paths too many. Interesting. Yeah, let's do some side-by-side comparisons. I hope we can do that. Yeah. So start ACA, BA, and it's already a bit tricky. I'm just gonna do this a bit differently. I'm gonna print out a string exactly as the example does it. So that is comma separated and just a cave name. Okay. So big cave gives us just a cave name. Small cave gives us just a cave name. Yeah. The compiler is correct. It's a path, not a single cave. So let's grab those cave names. Now we have all the cave names. Let's concatenate those with a comma. And probably this is a bit more readable. Yep. And let's print those out on a neat new line so we can start taking a look at what the problem actually is. There we go. Start A, B, A, C, A, and wait, we have 13 on this side, 10 on this side, so we have probably 3 more paths than actually necessary. So let's start taking a look at the left and comparing it with the right. A, C, A, B, A, and I see that one in there. I'm just gonna grab... No, it's okay. And then ACABD. ACABD. Is this in... This doesn't end. Oh, okay. I understand our bug. We generate all paths until we cannot generate a longer sequence anymore. But not every path in this list ends at the end node. Okay, yeah, that makes sense. So we are including dead ends. Dead ends suck, which is probably... Yeah, this is the case. We don't want anything in this case. Let's just return an empty array of paths. Dead ends... Yeah, dead ends are useless. So let's take a look now. Okay, do we have our magical number 10 this time? We do. I think we are good. I'm gonna keep this debug code around. So these are all the paths we find, and if we print out the number of paths, that's our puzzle answer. Sorry. There we go. Will we go big or go home and just running this on our input? I guess we will. We have more examples if things blow up. I'm going to do one more thing. I'm going to... Oh no, never mind. I was thinking maybe I should clean up my stuff a bit. Now it's just one hacky script instead of an actual program, but I don't really care. What I care about is whether or not this number is the correct answer. First time right. That's a bit of a shame, actually. We had a lot more examples, but maybe part 2 will redeem us in the negative sense of the word. What is it? Irredeem us? Condemn us? I don't know. But anyway, that was part 1. Let's take a look at part 2. I'm going to do my same thing, just copy paste it and forget about part 1 for the rest of the day. There we go. We have part 2 set up. What do we want? After reviewing the available paths, you realize you might have time to visit a single small cave twice. Only one. Only one small cave we can visit twice. Cool. Specifically, big caves can be visited any number of times. A single small cave can be visited at most twice, and the remaining small caves can be visited at most once. Okay. However, the cave's name start and end can only be visited exactly once. Once you leave the start cave, you may not return, and once you reach the end, you must end. That's a small twist, but an interesting one. Okay, the question is clear. How many... Sorry, let's go back one more time. How many examples do we have? Okay, we have all 3 examples worked out for part 2. So we are looking for the magical number 36 for the example we have been working with up until now. And yep, we did not need a list of caves, so let's get rid of that. Okay, so small minor detail, which is this thing. Small caves visited. There can be, but does not have to be, one small cave we can visit twice. How will we do this? So every time we encounter a small cave in the neighbor list, so down here, we have to make a decision. Will this small cave be the cave we visit twice? Yes or no? Or we can just keep doing what we have been doing. But we also always need to make that decision. If we have not yet visited a small cave twice, we have a choice. Or we visit this small neighbor cave we have right now. And that has to be the one and only small cave we visit twice, or we say no. Does that make sense, what I'm saying? Are there scenarios where not greedily selecting the first small cave will give a different path? I think so. Let's maybe do a quick doodle. So we are talking about small caves. Let's draw some out. A, B, C, A. I don't know. I'm just doing stuff here. But let's see here. If we are at A and we look at neighbors, those are both small caves. If we first say we visit B twice, we could go there, and back again, and then escape. But if we say let's not visit B twice, but let's visit it, yeah, that I think that will lead to different paths. How do we model this? I think if we make our small caves visited bookkeeping a bit smarter and model that choice I'm talking about, like do or not do, or treat this simple, small, that's the word I'm looking for. Yeah, we have to do a bit smarter bookkeeping, and I'm gravitating towards using an extra variable, like the variable indicating, oh, we have visited a small cave twice already. Or instead of a set, we could keep a set of caves and number of visits, but there's an invariant on that set that there can only be one small cave that can be visited twice. All the other ones must be visited once. Not sure which is the best approach. There is no best approach, so let's do something. Let's say we use a Boolean, an extra bit of bookkeeping, a Boolean. And the Boolean represents we have visited a cave. I don't know if we care which cave, but let's have a Boolean saying we visited a small cave twice. So let's provide that argument into the initial call. In the beginning, we have not visited a small cave twice. Okay, there were edge cases for start and end cave as well. Yeah, we do need to take that into account. What changes to the algorithm? Actually, this changes as well. We have to keep growing the set. Yeah, but we can't just throw away these because we could visit one a second time. Brain is completely blanking right now. How do we figure this out? Come on. So these are all the neighbors, and in part 1 we throw away every small cave we have already visited. Now we still have to do that, but we can make an exception one time. I'm not sure how to proceed, so I'm going to take really small steps here. So these are all the neighbors given current cave has. And then what are we trying to express here? All the neighbors we can visit. And that has changed somewhat. This filter is too strict now. This is still the case if we have visited a small cave twice. Otherwise, this changes. Yeah, I think we can get there by using that logic. So if we visited a small cave twice already, then it's the original thing. Otherwise, we have visited a small cave, or we have not visited a small cave twice, then we can just go anywhere. But we need to remember no, we don't need to remember anything here. We need to remember something down here, whether or not this will be the second visit. This is still the case. Yeah. So otherwise, for all the potential neighbors, we need to do stuff, yes, but these things will change. Yeah, these things will change, whether or not it has been a small cave, or whether or not we have visited a small cave twice already. Yeah, it's starting to make a bit more sense. I think it might not be the best algorithm, but we'll take it one step at a time. So neighbors, is this still correct? If we have visited the cave twice, we just take all the small caves, or all the caves except small caves we have visited, yeah, and otherwise we take a look at all the neighbors, yeah. Okay, and then for all the neighbors we do something, we find paths recursively, and these two things will change, yeah. So let's do the if thing again. Visited small cave twice. What happens if we have visited a small cave twice? Don't think that changes anything. I'm not sure of the part I'm doing right now. I'm just trying stuff out, actually. Otherwise, where do we need to do something differently here? Is this the magic spot? And have I even broken my auto formatter? No, we have not. Okay. So I think once we process a neighbor, and now we have to take a look at, we're in the case where we have not visited the small cave twice before, but we might have done that just now. So yeah, I think here we need to so if n is in the set of if it's in the set of already visited caves, we have visited the cave twice, and we need to bubble down that fact. And inserting it twice into a set, that won't hurt. No, I think this is maybe it. Does this if else make sense now? So this is true. If we have done this already. Yeah, I'm not gonna touch it. I'm tired. I've been coding for an hour. I'm not sure if we can simplify it, but let's first make it work, then make it right, and then maybe if we need to make it fast. Brilliant quote by Ken Beck, and I stand by it for today's puzzle. Yeah, maybe let's run the example again before we try to do the complete thing on our input. Let's take a quick look here. That's still reasonably fast. I spoke too soon. My computer is off digging for paths, I guess. Does that mean we have an infinite loop? Oh no, actually, it's not stuck. Huh? Cool, it's working. But is it correct? 63, is that the correct answer? Those are the correct digits, but not in the correct order. That's a shame. Oh yeah, start and end can be visited exactly once each. I don't think we take that into account. No, that could be probably our seeing. So start and end cannot be visited twice. Where do we fix that small oversight? Here. So if we have visited a small cave twice, then nothing changes. But if we have not, or actually no, we need to be able to reach end. So end has to be in here. Correct. Start doesn't have to. Yeah, let's get rid of start here. That doesn't work. Why does that not work? Okay, it works. Just missed some parentheses. So yeah, we never need to go back to start. That's true. But how do we get rid of... Oh, actually, no. Why are we hitting end multiple times? If current cave is end, we should be stopping. Do we have a case where we go back to start? I don't see any, Oh, yeah, there we go. We have returns to start. We cannot have returns to end because of this. We cannot have returns to start because of this. This might actually be the bug fix we are looking for. So we need 36, not 63. That would be nice. Thank you. Oh, first time right. Could it be? Let's take a look. It's not first time right. We already had a bug. Cool. I'm starting to get really hungry here, so I hope this is the correct answer. That's still not the end of the world performance-wise. That is a very big number. And it's the right answer. Cool puzzle. I really like the twist about visiting twice and not visiting small caves more than once. That was a cool constraint. Yeah, this was Advent of Code day 12. Let's take a quick look at what we did today. So we were doing a graph traversal algorithm. We did not need to find some kind of shortest path. No, we needed to find all paths, but there were some constraints on how many times we could visit a node, which we modeled by using a union type, a discriminated union, to make it easily, so we could handle it in our code a bit better, the two different cases. This is just some parsing. If I do like graph traversal algorithms, I like to build a map or a lookup table mapping a node to all the neighbors it can traverse to. If you do it like this, you can also like do directional graph, stuff like that. And this was the algorithm. We are doing a... What are we doing? A depth first algorithm? I think so. Because we recursively descend for a single path. Yeah, I think we're doing depth first. Took me a while to figure out the end condition, but I think it makes sense now that I see it. And if we're not at the end condition, we just look up possible next steps or next caves we could visit. We have a bit of bookkeeping to not visit small caves more than once or more than twice with the part 2 thing. Part 2 we did with a Boolean flag. That does not look very elegant, but it works. Then there's a little bug we had with the revisiting the start cave, which we should not be doing. If we cannot go anywhere anymore, we have found a dead end, so that's nothing. If we have found the end, that is a valid path, so we return that. And otherwise, we do recursive magic by doing something for every neighbor. And here we make the decision. Oh, hey, actually, is this correct? Yeah, because this set will only contain small caves. That's why this check works also for large caves or big caves. I was confused that I did not see the mention of a small cave here, but actually this magical line and that magical insert function we wrote, that will have it line up so only small caves end up in this set. So yeah, we make a decision, like we branch into two parallel universes, one where we, if it's a small cave, visit it for the first time. Second time, this is where we do the multiple worlds interpretation kind of thing, or where we branch off at least. And then we just call this recursive function, and that's it. Cool puzzle. Enjoyed it. I hope you did too. And I will see you tomorrow for Advent of Code in F#. Bye bye. Let's maybe take a quick look if we have someone to raid. No, it's quiet today. We only have Anthony. Yeah, let's board the raid train and let's go take a look at what Anthony's been doing. Okay, we're gone in 3 seconds. So all aboard the raid train and let's go.